So in the last classes, we discussed about the realization of digital filters, right? That is third unit, the realization of digital filters. So in that we have the IIR filter, FIR filters, okay, recursive filter and non-recursive filters, and are the techniques techniques for individual model. Okay, we are going to discuss about the FIR filter and realization of the FIR filters. Okay, FIR filters and its realization. So, how the filter is different. Filter is a frequency selective system. It is a frequency selective system. So, digital filters are classified as a finite duration unit impulse response, that is FIR filters, and infinite duration impulse response filters, that is IIR. Finite duration unit impulse response system are referred as FIR filters, and infinite duration unit impulse response filters are referred as IIR filters. Okay, so like these filters are classified into FIR and IIR filters. FIR means finite duration unit impulse response filter, and infinite duration unit impulse response filter is IIR filter. So depending upon the form of unit impulse response of the system, that depends upon the form of unit impulse response of the system. So in the FIR system, the impulse response frequency is of finite duration. So that is fine. That's why it is called finite duration unit impulse response system, or finite duration unit impulse response filter. Okay. Okay. Right. So, similarly, in the IIR system has an infinite number of non-zero terms. Okay. IIR filters are usually implemented using recursive structures. Recursive IIR filters are, these are also called as recursive structures. Recursive structure means feedback poles and zeros. It includes feedback poles and zeros. And FIR filters are usually implemented using non-recursive structures. Non-recursive means there is no feedback, only zeros are included. Okay, only it includes zeros. Okay, right. So the response of the FIR filter depends only on the present input and past input samples. FIR means present input and past input, whereas the IIR filter response depends upon present input, and past output also. Okay, present input and past output samples. Okay, the present output of the IIR filter depends upon present input, and past output, whereas the response of the FIR filter depends upon present input and past input samples. Okay, so FIR filters have no feedback. FIR filters doesn't contain any feedback; it contains only zeros, whereas IIR filters contains feedback, zeros and poles. Okay, now now we'll see the advantages of FIR filters over IIR filters. Okay, so these FIR filters are recursive, non-recursive structures, whereas IIR filters are implemented using recursive structures. Okay, now we will see the advantages of FIR filters over IIR filters. Okay, finite duration. FIR means finite duration. IIR means infinite duration. Unit impulse response filters. Okay, so finite duration unit impulse response filters over infinite duration unit impulse response filters is the advantages of FIR filters over IIR filters are FIR filters are always stable. Okay, next FIR filters with linear phase exactly linear phase can easily be designed. That FIR filters with exactly linear phase can easily design. FIR filters can be realized in both recursive as well as non-recursive structures. FIR filters can be realized in both recursive as well as non-recursive structures. FIR filters are free of limit cycle oscillations when implemented on a finite word length digital systems. Okay, FIR filters are free of limit cycle oscillations when implemented on finite word length digital systems. And excellent design methods are available for various kinds of FIR filters. So these are the advantages of FIR filters over IIR filters. Coming to the disadvantages of FIR filters are the implementation of narrow transmission band FIR filter is very costly, as it requires more. Okay. So arithmetic operations and hardware components such as multiplier, adders, delay elements, arithmetic operators and hardware components such as multipliers, adders, delay elements. Memory requirement and evaluation time are very high. So these are the disadvantages of FIR filter when compared to IIR filters. Next comparison of IIR and FIR filters. Compare the IIR and FIR filters. So all the infinite sample of impulse responses are considered in IIR filters. Only finite number of samples of impulse responses are considered. Next, when the impulse response cannot be directly converted to digital filters transfer function. So the impulse response can be converted to digital filters transfer function in FIR filters. In IIR, linear phase characteristics cannot be achieved. Whereas in FIR filters, linear phase filters can be easily designed. Okay, IIR filters are easily realized recursively. FIR filters can be realized recursively and non-recursively. Okay, so next the specifications includes the desired characteristics for magnitude response only. And here the specifications include the desired characteristics for both the magnitude and phase responses. So here in FIR filters, the design involves design of analog filter and then transforming analog filters to digital filters. Design involves the design of analog filters and then transforming analog filters to digital filters. Here in the FIR filters, the digital filter can be directly designed to achieve the desired specifications. It can be directly designed. Whereas here in IIR filters, the design of analog filter involves the design of analog filter and then transform into analog filter to digital filters. Okay. Next, last comparison is the round of noise in IIR filters is more. Errors due to round of noise are less 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 response in FIR filters, mainly because of feedback is not used in FIR filters, whereas feedback is used in IIR filters. That's why the round of noise is more, whereas the round of noise is less in IIR filters. Next, coming to the characteristics of FIR filters with linear phase. Okay, characteristics of FIR filters: finite duration, unit impulse response filters, that is FIR filters. So characteristics of FIR filters with linear phase. Okay. The transfer function of FIR causal filters is given by h of z equal to sigma n equal to 0 to n minus 1, h of n into z power minus n. This is z transform. H of z equal to sigma n equal to 0 to n minus 1, h of n into z power minus n, where h of n is the impulse response of the filter. Now the frequency response, that is Fourier transform of h of n, is given by h of omega is equal to sigma n equal to 0 to n minus 1 h of n into e power minus j omega n. Okay, impulse response, frequency response is nothing but Fourier transform of h of n, right? Frequency response is nothing but Fourier transform of h of n. That is this is for discrete time signal, that is h of omega equals sigma n equal 0 to n minus 1 h of n into e power minus j omega n. It is equal to, it can be represented as h of e power j omega. Okay. Since h of omega is complex in nature, it can be expressed as h of omega is equal to mod h of omega into angle of h of omega, mod h of omega into angle of h of omega. Okay, where mod h of omega is nothing but magnitude response. Okay, and here we are introducing plus or minus here. So h of omega equal to plus or minus mod h of omega into angle of h of omega, where mod h of omega is the magnitude response and theta of omega is angle of h of omega, right? So h of omega equal to plus or minus mod h of omega into angle of h of omega e power j theta of omega, e power j theta of omega. So theta of omega is phase response. We define the phase delay Tp and group delay Tg of a filter as a Tp equal to minus theta of omega by omega and tau g, tau p is phase delay and group delay is tau g. So tau g is equal to minus d by d omega of theta of omega, right? d theta of omega by d omega. Okay, for FIR filters with linear phase, we can define theta of omega is minus alpha into omega, but minus pi is less than omega is less than pi. So we can write this as tau p is equal to minus of theta of omega. So actually theta of omega is minus alpha omega. This can be replaced by plus alpha omega by omega. It is equal to plus alpha. And tau g equal to minus d by d omega of minus alpha of omega. So plus d alpha omega by d omega. So d omega gets cancelled. It is equal to alpha plus alpha. Here tau p equal to tau g equal to alpha, which means that alpha is independent of frequency. Okay, alpha is independent of frequency. Okay, so h of omega is equal to plus or minus mod h of omega into e power j theta of omega. Okay, so sigma n equal to 0 to n minus 1 h of n e power minus j omega n is equal to plus or minus mod h of omega into e power minus j theta of omega is e power j theta of omega is minus alpha omega. So it will become e power minus j alpha omega. Okay, e power minus j alpha omega. Then sigma n equal to 0 to n minus 1 h of n into e power minus j omega 1 n can be written as cos omega n minus j sin omega n is equal to plus or minus mod h of omega into e power minus j alpha omega is cos alpha omega minus j sin alpha omega. Okay, and equating the real part and imaginary part of the above equation, we get this is equation number 1. So equating real part and imaginary parts of the above equation, we will get sigma n equal to 0 to n minus 1 h of n into cos omega n is equal to plus or minus mod h of omega into cos alpha omega. Okay, cos n alpha omega, cos alpha omega. Okay, that is equation number 2. And imaginary part is sigma n equal to 0 to n minus 1 h of n into sin omega n is equal to plus or minus h of omega into sin alpha omega. This is the imaginary part. And dividing the equation 3 by 2, sigma n equal to 0 to n minus 1 h of n into sin omega n by sigma n equal to 0 to n minus 1 h of n into cos omega n is equal to plus or minus h of mod h of omega into sin alpha omega by plus or minus mod h of omega into cos alpha omega. So it will become tan omega n sin omega n by cos omega n equal tan omega n. Okay, and this is a sin of alpha omega by cos alpha omega is tan alpha omega. Okay, so sigma n equal 0 to n minus 1 h of n into sin omega n into cos alpha omega is equal to sigma n equal 0 to n minus 1 h of n into sin alpha omega into cos omega. Okay, so it is equal to sigma n equal 0 to n minus 1 h of n into cos omega n into sin alpha omega minus sigma n equal 0 to n minus 1 h of n into sin omega n into cos alpha omega is equal to 0, or we can take sigma n equal to n equal to 0 to n minus 1 h of n as common. So it will become sin alpha omega into cos omega n minus cos alpha omega into sin omega n, which is equal to 0. We can write this as sin a cos b minus cos a sin b, that is sin a minus b, right? So sigma n equal to 0 to n minus 1 h of n into sin a minus b, that is sin alpha omega minus omega n is equal to 0, or it is sigma n equal to 0 to n minus 1 h of n into sin alpha minus n into omega is equal to 0. This is equation number 4. One solution of equation number 4 is an alpha equal to n minus 1 by 2 and h of n equal to h of n minus 1 minus n. Okay, h of n equal to n minus 1 minus n, for 0 is less than or equal to n is less than or equal to n minus 1. Okay, so h of n into sin alpha minus then to omega, that is h of n into sin n minus 1 by 2 minus n alpha is n minus 1 by 2 minus n into omega. So n minus 1 minus n minus n by 2 into omega. Alpha is n minus 1 by 2. Write this as this will get sin 0 sin 0 sin 0 in n minus n by 2 into omega, that is sin 0. This shows that FIR filters will have constant phase and good delay. Impulse response is symmetrical about alpha equal to n minus 1 by 2. The impulse response satisfying the symmetric condition h of n equal to h of n minus 1 minus n for odd and even values of n is shown in graph. Okay, when n equal to 9, then the center of the symmetry of sequence occur at fourth sample, and when n equal to 8, the filter delay is 3.5 samples. Okay, so n is 9, that is odd. 1 0 1 2 3. Center of frequency is 4, that is n minus 1 by 9 minus 1 by 2, that is 4. So when n is even, the center of the symmetry is 0 1 2 3. That is between 3 and 4. 3 and 4. That is n by 2 minus 1. That is 8 by 2 4 minus 8 by 2 8 by 2 4 minus 1 3 and 4. It is in between n by 2 minus 1 1 and n by 2. So that is the center of symmetry. So here, case first of all, we will see the case 1. If only constant group delay is required and not the phase delay. First case is if only constant group delay is required and not the phase delay. Okay. Not the phase delay. Then theta of omega equal to not if there is no phase delay. Then theta of omega will become beta minus alpha omega. So tau p will become phase delay. Tau p will become minus theta of omega by omega, but theta of omega is minus alpha omega. So minus alpha beta minus alpha omega by omega. So it will become alpha minus beta of omega. It is not a constant. Okay. Next group delay tau g equal to d by d omega of theta of omega. So theta of omega is beta minus alpha omega. Okay, minus d by d omega of beta minus alpha omega. It is equal to minus d by d omega of beta, that is 0, minus some minus plus d alpha omega by d omega. So it will become alpha, it is some constant. Okay. So h of omega equal plus or minus mod h of omega into e power j into theta omega. So sigma n equal 0 to n minus 1 h of n into e power minus j omega n is equal to plus or minus mod h of omega into e power j theta omega is beta minus alpha omega. Okay. So if sigma n equal 0 to n minus 1 h of n e power minus j omega cos omega n minus j sin omega n is equal to plus or minus h of omega into e power j beta minus alpha omega is cos beta minus alpha omega plus j sin beta minus alpha omega. Equate real and imaginary parts so that it will become sigma n equal 0 to n minus 1 h of n into cos omega n equal plus or minus h of omega cos beta minus alpha omega. Similarly, minus sigma n equal 0 to n minus 1 h of n into sin omega n equal plus or minus h of omega into sin beta minus alpha omega. So equating dividing equate 7 by equating 6, we will get minus sigma n equal 0 to n minus 1 h of n into sin omega n by sigma n equal 0 to n minus 1 h of n cos omega n is equal to plus or minus h of omega into sin beta minus alpha omega by plus or minus h of omega cos beta into alpha omega. Okay. So by cross multiplying, we'll get minus sigma n equal 0 to n minus 1 h of n sin omega n into cos beta minus beta minus alpha omega equal sigma n equal 0 to n minus 1 h of n cos omega n sin beta minus alpha omega, or cos omega n into sin beta minus alpha omega plus sigma n equal 0 to n minus 1 h of n into sin omega n cos beta minus alpha omega equal 0, right? So it is in the form of cos a sin b plus sin a cos b, that is sin a plus b. So it is equal to sigma n equal 0 to n minus 1 h of n into sin omega n plus beta minus alpha omega equal 0, or equal to sigma n equal 0 to n minus 1 h of n into sin omega into n minus alpha, okay, plus beta. So here omega is common, omega taking omega is common, n minus alpha plus beta is equal 0, or sigma n equal 0 to n minus 1 h of n into sin beta minus alpha minus n into omega equal 0. If beta equal to 5 by 2, then it will become sigma n equal 0 to n minus 1 h of n into sin 5 by 2 minus alpha minus n into omega sin 5 by 2 minus theta, that is equal to sigma n equal 0 to n by 2 h of n cos alpha minus n into omega is equal to 0. So this equation will be satisfied when alpha equal to n minus 1 by 2 and h of n equal to h of n minus 1 minus n. This shows that FIR filters are constant with delay tau g equal to alpha and tau p is equal to not constant, and the impulse response is antisymmetrical about alpha equal to n minus 1 by 2. Okay. So here the impulse response satisfying the antisymmetrical condition is shown in the following figure. When n equal to n, the center of the antisymmetrical antisymmetry occurred at both sample, and then n equal to 8, the center of antisymmetry occurs at the end of sample. The center of the symmetry, center of antisymmetry for n equal to 8, for n equal to 9. Okay. So you see the frequency response of the linear phase FIR filters. Frequency response of linear phase FIR filters with first of all we see frequency response of linear phase FIR. Okay. So the frequency response of the filter is the Fourier transform of its impulse response. Basically, the frequency response of the filter is the Fourier transform of its impulse response. That is Fourier transform of H of n. Say, okay. So if H of n is the impulse response of the system, then the frequency response of the system is denoted by H of z. That is R H of omega, H of e power j omega, or H of omega, right? H of omega is a complex function of frequency omega and it can can be expressed as magnitude function mod H of j omega, and phase function angle of phi of j omega. Okay. So frequency response can be expressed as a function of magnitude and phase. Okay. Magnitude is mod H of j omega and phase angle is angle of phi of j omega. Okay. Depending on the value of n, if n is odd or even, and the type of symmetry, response of the filter impulse response sequence, that is symmetry and antisymmetry. There are following 4 types of impulse responses for linear phase FIR filters. Here we have 4 types of impulse responses for linear phase FIR filters. So first one is frequency response of linear phase FIR filter when impulse response is symmetrical. Okay. Frequency response of linear phase FIR filter when impulse response is symmetrical and n is odd and n is odd. Okay, that is the first case. Here, HFN with the impulse response of the system. The frequency response of the system H of omega is given by H of omega equal to H of e power j omega is equal to sigma n equal to minus infinity of n to e power minus j omega n is equal to sigma n equal to 0 to infinity. So here we'll take the limits from 0 to infinity only. Sigma n equal to 0 to infinity H of n into e power minus j omega n, and n is odd. H of n is symmetric center of symmetry at n minus 1. Okay, n minus 1 by n minus 1. Okay. So here we'll write this expression as sigma n equal to 0 to n minus 1 by 2 into h of n into e power minus j omega n plus h of n minus 1 by 2 into e power minus j omega into n minus minus 1 by 2 plus sigma n equal to n plus 1 by 2 to n minus 1 h of n equal to e power minus j omega n. Right. Symmetry at n minus 1 which can be written as sigma n equal to 0 to n minus 1 by 2 h of n equal to e power minus j omega n plus h of n minus 1 by 2 into e power minus j omega n minus 1 by 2 plus sigma n equal to n plus 1 by 2 into by n equal to n plus 1 by 2 to n minus 1 h of n equal to e power minus j omega n. Here n equal to n minus 1 minus n and small n equal to from this small n will become n minus 1 minus n and n equal to n plus 1 by 2 then n will become n minus 1 minus n plus 1 by 2. So n equal to n minus 1 then n will become n minus 1 minus n minus of n minus 1 0 e. So h of n equal to sigma n equal to 0 to n minus 1 by 2 n minus 3 by 2 h of n into e power minus j omega n plus h of n minus 1 by 2 e power minus j omega n minus 1 by 2 plus sigma n equal to 0 to n minus 3 by 2 into h of n minus 1 minus m. Okay. Into e power minus j omega into n minus 1 minus m. M equal to m. This expression. So this derivation we will see in the next class. With this I am concluding the today's class. Okay. So continue in the next class. Next class we will again discuss this.